Welcome back. In this lesson we are going to learn about how the fission neutrons are sampled in Monte Carlo transport simulation with the implicit capture method. In the previous lesson I have introduced the very popular implicit capture method. The implicit capture method does not simulate the absorption reaction explicitly, and only the scattering reactions are sampled. So at every collision point we do not need to sample the reaction type. We know the reaction will always be scattering, and we adjust the statistical weight of the neutron to compensate for the changes in the probability for choosing the reaction types. So we sample a number of scattering collisions until the neutron weight drops below the weight limit, or until the neutron escapes from the system. So if the neutron escapes, we can terminate the simulation. Now, at every collision point we adjust the statistical weight to compensate for the changes in the sampling rules. We multiply the statistical weight by the factor sigma s divided by sigma t, the probability that the scattering reaction occurs in analog simulations. Now you may wonder, if we only simulate the scattering reaction during the whole neutron history, how do we actually sample the new fission neutrons? We need to sample new fission neutrons in a fissile system. For instance, in criticality calculation we need to generate new fission neutrons in order to have the fission source for the next criticality cycle. The solution to this problem is actually very simple. The implicit capture method accounts for the fission reaction implicitly. It implicitly simulates the fission reaction at every collision point. So every time the neutron collides, the fission reaction accounts for a certain decrease in the statistical weight of the neutron. That follows from the fact that we multiply the weight of the neutron at every collision point with the ratio sigma s to sigma t. The total cross-section equals the sum of the scattering cross-section plus the absorption cross-section, and the absorption cross-section combines the cross-section for the neutron capture and the fission cross-section. So the bigger the fission reaction is, the bigger the total cross-section is, and the smaller this ratio is. So in a fissile system, part of the drop of the neutron weight at every collision accounts for the fission reaction. Nevertheless, we need to sample the fission neutrons as well. So because the fission reaction is reflected into every scattering point here, we can try to evaluate the expected number of fission neutrons at every collision point. So I'm going to be denoting the expected number of fission neutrons at a certain collision point by the S bar quantity here. Of course it is dependent on the neutron energy, because we have to reflect the probability that the fission reaction occurs at a specific collision point. We also need to reflect the statistical weight of the neutron at this collision point into this number. And I'm going to show you two ways how you can estimate this number in the next slides. Now you need to realize that this expected number of fission neutrons may be a very small number, because the statistical weight of the neutron, the parent neutron, is reflected into this number. So especially when you evaluate these expected number of fission neutrons at the end of the neutron history, the statistical weight of the neutron history may be very small by that time, and therefore the expected number of fission neutrons that you simulate, for instance, at the last collision point, may be very close to zero. The number may be 0.001, for instance. So, of course, we cannot sample new fission neutrons at every collision point. We would end up with having a huge number of fission neutrons with very small statistical weights. We, in principle, need to generate, on average, just one fission neutron during the whole neutron history. So we need to decide the whole number, right, the integer number, based on the expected number of the fission neutrons at every collision. So at every collision, we first evaluate the expected number of fission neutrons, and based on this number, we decide whether we actually simulate the fission neutron at that point or not, right? So you can imagine, if this number, the expected number of neutrons, is very small, very close to zero, there is a very little chance that we will eventually decide to start a new fission neutron at that point. So I'm going to have one slide at the end of the presentation about how do we actually decide whether we sample the fission neutron at the collision point or not, and in case we do, how many fission neutrons do we generate there. In order to estimate the expected number of fission neutrons at every collision site, we can use two types of estimators. One of them is called collision estimator, and it's fairly straightforward. As you can see, the collision estimator takes the probability that a fission reaction occurs in the collision point. So that is this ratio of the fission to the total cross-section for the specific nuclide that was selected. And this probability is then multiplied by the average number of fission neutrons. So this is an experimentally measured number. For uranium-235, it's approximately equal to 2.45. And this is then multiplied by the statistical weight of the neutron that collides at the point. The next estimator that we can use to estimate the expected number of fission neutrons is called the track length estimator. It's also called the path length estimator, and it estimates the expected number of fission neutrons according to this formula. It's a product of four factors. The first one is the statistical weight of the neutron. The second number here, S, is the distance between the last two collisions. The next number is the nu number, the number of fission neutrons in real fission. And the last number is the macroscopic cross-section for fission. Now, the idea of the track length estimator may not be obvious at first, so let's have a look at the example. I will draw two successive collisions here. So let's try to evaluate the number of neutrons, the expected number of fission neutrons at this collision. So when you look at the formula here, you see that the macroscopic cross-section for fission is multiplied by the distance between the last two collisions. So that's this number S here. Now, the macroscopic cross-section for fission actually has a very nice meaning in non-analog simulation. It gives the expected number of fission reactions per unit of distance. So when you multiply this with the distance between the last two collisions, the product of S times the sigma F will give you the expected number of fission reactions along the path from the last collision to the current one. So this way the track length estimator actually tries to minimize the random noise which is coming from sampling of the distance between two collisions. You see, the distance between collision is a random variable. It's given by its probability density function. So if this distance by chance is sampled very large, then the track length estimator will actually account for it, and it will increase the expected number of fission neutrons which would be sampled in the collision. If this distance is sampled very small, then again the track length estimator would account for it, and it would reduce the expected number of fission neutrons at that collision site. It's hard to give any recommendation as to whether the track length estimator can give better results than the collision estimator. The track length estimator may have a little smaller noise when sampling the fission neutrons. However, you will probably not notice this in normal criticality calculations in which you simulate thousands of millions of neutron histories. Once we estimate the expected number of fission neutrons at a specific collision site, we need to decide on the real number of the fission neutrons that we actually sample at that site. So let's take an example. For instance, we can estimate the expected number of fission neutrons to be a very small number, 0.1. Typically it will be a small number. So when you look at this small number, 0.1, you can see that we are more likely to sample no fission neutrons in this collision site. Actually, we can see that the chance that we sample one fission neutrons is only 10%. So with the probability 10%, we sample one fission neutrons, and with the probability 90%, we sample no fission neutron. So you can take this data and you can simply use the inverse transform method to sample the value to the number of neutrons, the S number. Now the same result you will obtain if you use this equation to sample the real number of fission neutrons. So in this formula you can see that the expected number of fission neutrons is combined with the random number generated within the interval 0, 1 from the uniform distribution, and that is then taken by the int function, which returns the closest integer number to x, so to this sum of the expected number and the random number from the random number generator. It's closest integer number which is lower than x. So let's take the example that we have here. The expected number is 0.1, so I will draw it like this, 0, 1. So our expected number is here, 0.1. Then we generate randomly the random number from the interval 0, 1. So let's say that I generate number 0.5. So when I sum it up with 0.1, that will give 0.6. Then I will apply the int function on it. So the closest integer number to 0.6, which is smaller than 0.6, is 0. So in this case I will end up with 0 fission neutrons. So I would sample one fission neutron only if the random number is bigger than 0.9, right? Only in that case the sum of the random number and my expected number of fission neutrons would grow above the number of 1. So in that case the int function would return number 1. So that corresponds very well with our results here. And that is all for now. Have a nice day.